Hello world, what's up? My name is Brendan and welcome to the channel. Today we're going to be talking about one of the most exciting parts about this ant class. Don't go away. It's going to be the brain class, the neural net, and basically how these guys actually know how to move around. And the big question for this is, did I program all that? And the resounding answer is no. They're figuring it out by themselves. Essentially, when they first start out, they're initialized with a random weight of matrices, and yeah, we're going to go ahead and we're going to see all that and how that works in actual code. So without any further ado guys, let's get jumping into it. Quick note before we start, if you guys want to check out the playlist, see any of the other examples on this, I've covered the ant game, how we're getting set up. Okay, let's jump into it. So as you know, each ant needs to have some sort of input. It needs to know how to move around the world. When I was first developing it, I just gave them a random walker function, which is essentially pick a certain number between a random Gaussian, right? It starts off with a mean of 0 and plus or minus 1, and then they go, okay, I want to go 1 in this direction or not 1 in this direction, and it was just a random class. But we won't be talking about that today. We're going to be talking about the brain input. The only reason I bring it up is because both brain input, random input, and player input are all extending this wrapper component, which is essentially input component. So ant class only knows how to talk to an input component. It doesn't know exactly what a brain input is. It just cares when I call update, the update's going to return, hey ant, you should move so much in this direction, or you shouldn't move in this direction, or you should do this with your mouth. So that was all programmed into the random. Hasn't been implemented yet in the player, although it will be possibly at some point in the future if I decide to pick up this project again. But yeah, that's why we talk about it. All right, cool. But what is so important about this brain class, and what makes it different from a random walker, and what makes it different from a player input? Well, I think that last one's pretty obvious. We're not in the game, right? We're not programmed into here. So we need to program something called a neural network, and that's what we're going to get into. All right, so float. So this basically is saying, hey, I'm going to have some outputs, I'm going to have some inputs, and you know what, it's down here. It's down here, I got it down here. There we go. So I'm not going to, 19 of them. So I'm not going to write them all out because you guys can see them here, and that's awesome. So the first input, hey ant, you know, what's your size? Are you of breeding size, right? Are you not of breeding size? Are you close to death? Are you massively fat, right? What's your size? And the neural network at one point, hopefully is going to care about this, or maybe it won't. I don't know. It can learn to shut off and activate different inputs and pass those along to its outputs, right? And we'll see right away what it's doing with those outputs through the neural network and how it takes these inputs and translates them into different actions that it should take. But first, let's just go ahead and cover what the ant can actually sense around the world, because it's not like you and I. It doesn't have eyes, it can't see, so we have to program in all of these different things. So get bite size, you know, what's your current mouth size? So the ant can actually change, I believe it can change how much it's going to bite per tile. I think the maximum is 3, so that's why I put it here as 0 to 3, although this really should be changed up to one of our constants. What we learned in the global session there is, I think, max bite size. Pretty sure that's going to be it. Yeah. Maximum bite size. Okay, so bite size is maximum, but it can't be changed by them. Possibly. But that's something to figure out. That's a question for us. All right, get the world temperature. These ants have a sense of how warm it is, just like you and I. And just like ants in the regular world, they've got a sense of how warm it is. They'll know if their favorite food is dying, perhaps, or if it's not dying. But they'll learn that, hey, maybe when I'm eating green grass and it's cold outside, they'll learn that I probably shouldn't be eating as much to preserve the grass, so I can have something to last me through the winter. What's their current energy? So energy is different from size. Is it really though? Can this be, one sec, can this be replaced by energy alone? I think it can. I think it can. And I'll tell you why. Because energy is linearly proportional to size. And I bring up the word linearly very specifically here because we're going to be talking about non-linearization functions later on in this. And even though it might sound like a scary word, essentially just means if I say in a linear function, if I say 0, you say 1. If I say 1, you say 2. If I say 2, you say 3, right? It's just a straight up, the input is going to be proportional in some way to the output, right? That's a linear function. It can be drawn in a straight line. A nonlinear function essentially means the input might not be exactly equal to the output. So that's why I'm saying that I don't think I need this input 0. I think that can be replaced because it's linearly proportional to this input 3. Our brain class would recognize these two guys as the same thing. Input 4. Now, okay, so here's what we're doing here. I think this all has to do with, I'm just going to pop this on down here. This all has to do with eating the grass. We are going to map. And by the way, you might see this function map here, wondering what it does. Essentially just takes, let's say this is my input between these two functions, and my output, I want it between, or sorry, my input maybe is between these two massive areas, and I want my output between these very two small 0 to 1, right? Because whenever we get into neural networks, they tend to perform better when we have, when we pass them data that's between a 0 and a 1. That's what it is. You know what? That's what it is. And this is why we do it. So let's say, and this is a very good example, we'll talk about a house for now, right? If we want to take, how many number of rooms, what's the square footage, what's the age of the home, and try to calculate the selling price. If you take all of these things, they're typically numbers between 0 and 100, except for square footage of a house. That could be a few thousand, could be multiple thousands. And if we're trying to have these weights, in which you'll see in a second how they take their input multiplied by the weight, activate. When they're multiplied by the weight, if we got one that's like 30,000 and others that are only 2 or 3, we're going to have a little bit of an issue there. So that's why we bring everything down and map it down between either -1 and 1 or 0 and 1. So that's what this map function is doing here. On our parent class, which is going to be our parent ant class, we are going to be asking for the difference between its mouth hue and the sensor at sensor 1, and the sensor now, the next line, input 5, will be at sensor 2, right? So if I've got a green mouth and I'm sensing green food off to my right and blue food off to my left, I'm going to be able to know the difference between those two, right? I'm going to be able to know, it's like, hey, this one has a very low difference here to my mouth, maybe perhaps I should go this way, or that's what we're hoping the neural net will learn into the future, right? It doesn't know that when we initially start, and you'll see that when we're finished covering this, we're going to go into the brain class and we're going to see exactly what I'm talking about. All right, bros, let's keep going. One sec. Love that water. Okay, cool. Keep the throat nice and moist, right? That's what I'm talking about. Okay, difference between hue and mouth hue and get underneath. So yeah, essentially for these three, for inputs 4, 5, and 6, we're talking about, what's underneath me? Does this match the color of my mouth? If underneath my body, if my mouth is green, is the food underneath me green, or is it blue? If it's blue, I don't want to be eating, right? If it's green, I want to be eating as much as I can, getting more energy. Helps me with breeding, helps me with surviving, helps me with a whole bunch of things, right? Moving on here, moving on. Input number 7, map saturation brightness. Okay, so tile underneath, tile information underneath. So the saturation and brightness, and these are going to be under our sensors. Yeah, okay. So saturation on the land, as you know, is how much food, how many noms, how many whatevers are on the land, can I eat it, right? So we're just checking underneath our sensor. Is there actually food over there? Is there no food? Is there actually food off to the left, or is there no food, right? So we have to check all these things. Saturation, brightness, and hue. And yeah, that's that. So it knows what's going on. Need saturation of tile underneath my face. So parent 1, feel F length 0, like 0, 1. Right. How far away? So these are just, again, to do with the feelers. Oh, this is very interesting. So let me just move these up here, because these all have to do with tile underneath feelers. So this is just checking out all the feelers, and then it's finding out what's the distance away from body. And I'm gonna put that up there. Remove that comment. Needs saturation of tile underneath the face. So the ant, this is very, very interesting. I didn't realize this. I didn't actually program a sensor underneath the body of the ant. It doesn't know what's underneath it. Hey guys, Future Brendan here. It actually doesn't know what the saturation is underneath it. It does know what the hue is underneath it. So we'll know if it's harmful or helpful, but it won't know how much food is actually underneath its body. So it needs to keep on moving continually. Okay, input 13. We're gonna map the velocity, its magnitude. Okay, so again, we're just mapping velocity between 0 and 1, seeing how fast we're going. Our bias always start at 1. Okay, that's kind of interesting. I don't know why I put this comment here. I can delete that. Parent feeler 1 rotation. Oh yes, we know in which direction it's heading. We'll know in which direction we're heading. And this could probably go down to a 0 or 1 as well, or -1 to 1 as well. And then we're going to map the world map, get the ant population. Oh, so they've got a sense. So I guess these are ants. I thought that maybe they're a community. They'll know how many ants are available in the world. And then world has another class on it called this world map, which has a characteristic called probable carrying capacity. And I think I create this as some function of the square area of the land minus the water, of course. So the ants do know, yeah, roughly how many ants are in there. And this is just, again, mapping between min ants, which I think I have set at 40 for the current map, and as a global as constant. Anything in capitals, by the way, I set as a constant, quote unquote. I don't think you can actually really have true constants in here, because I can go in here and I can change all these things, but when it's running, it's constant. I don't change them. Okay. If there's another birth ant nearby, all right. If my parent doesn't have a birth ant nearby, I'm going to set my input 19 as 0, running as false. Otherwise, I'm going to set it as true, 0 or 1. Very simple input. And input 20, I set as 1. Why? This is, I always want to have one input as 1, right? And this typically has to do with, you know what this has to do with backpropagation. And I want to remove input 0. You know what, I might as well just do that right now. Yeah, and then, yeah, and I'll remove input 20. And because I don't need that for forward propagation, because this network actually works a little bit differently than a neural network where you're going to be feeding forward information, training your data, saying, hey, is this number recognizing, do you recognize this pattern? It'll either say yes or no, or it'll give you a guess, and then we'll have to tell it, you know, I got a training set of data. Yeah, you got the answer right, or no, you got the answer wrong, and then we have to backpropagate through the system to train it. However, in a genetic algorithm, a genetic component, we don't backpropagate ever. This is all just the ants either learn to live, and then they'll be able to propagate themselves with a little bit of mutation, adding some variation into the society, or they die, and then in which case that was a bad neural net, their brains were bad, and they deserve to be killed off. So there you go. So we're getting rid of input 20 and we're getting rid of input 0, which is going to give me an error because I've said right now the current inputs, but you'll see when I set it up here, is equal to there we go, our input n, and our input n should be equal now to 18 plus 1, which would be 19. All right, so let's go into our globals, and we'll change our input n to 19. Input title, working for neural net, and specific GUI, nope, GUI under and specific, input n. There we go, neural net, boom. So we got rid of 2, we're down to 19. And remember, always 1 here for bias. Well, we don't actually need 1 because we are not backpropagating, and it's not important, and you'll see why in 2 seconds. Okay, so get rid of that. Don't need 1 at n because we don't backpropagate. All right, let's run this. Okay, awesome. I'm gonna drag this on over so you guys. Okay, so our program's gonna slow down quite significantly because we're making many draw calls. in here into the lower right hand corner for our neural network. What you can see here is now our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Our 19 inputs, which we just went over. Okay, and now you're wondering, well, what's this whole slew of a mess between the first kind of, let's call them these nodes, right? This first layer of nodes, and what's the slew of, and let's call these guys synapses between those, the first nodes and the second nodes. Well, these are synapses. These are a matrix of numbers between, I think, -1 and 1, although it could be larger or smaller, I think, but just barely, roughly barely. And essentially, this is our neural network. That's the important part. The synapses are the important part. The inputs aren't important. The middle parts are deterministic based upon these matrices, these synapses, and our outputs are also deterministic based upon these, the second layer of synapses. So these are two matrices here that we're looking at. The white band implies that it's a very strong connection. If if for instance, number 1 here, which I see set as a gray, which is I think a lower number, has a, well, let's go to number 2, input 2 here, right? Okay, we're gonna be bouncing back and forth between our inputs and this screen here just for 2 seconds, okay? So input number 2, what is that? It's white, right? So on this ant that I've got here, which currently just died, let's go back to our brain class. Let's go to input number, so not 0, 1. Let's go to input 1. Right. All right. Input 1. So get byte size. So its byte size is currently, I'm going to say 3 because it can't change it. I'm pretty sure it can't change it. We haven't looked at the outputs yet. Let's do that just for right now. Byte size. So these are the outputs that we get back from the brain querying the brain. It can tell it to eat or not eat, but it can't actually grow or shrink its byte size. But it does know how large its byte size is. Very interesting. And I wonder if, because it can't change it, is it even necessary to have the byte size in there? Probably not. Probably not. Anyways, but you can see that this is a white because its byte size was 3. We're mapping it between, let's go back to processing. Okay, so its byte size is 3, and we are mapping it between parent.get byte size, which is 3, between 0 max byte size, so it was 3. So it will be on the high end of this, so it will be a 1. Anything on this neural net that is a 1 is a white. Anything that on here is -1 is black, and get the whole range, and 0 would probably be this grayish color, right? If we click on something live, you can see all of these guys changing very quickly, but we're not going to do that because it's very nice to have this just very stationary to illustrate the point. So white synapse, very strong connection between the first node going through a white synapse, which would be like, multiply this by 1, not -1 or 0, to effectively cancel it out or shut this off from talking to something else. Multiply it by 1, and it's going to be lighting up something down here in our middle layer of nodes, right? These are our hidden nodes. Then exact same thing happens from our hidden nodes to our output nodes. Our hidden nodes get multiplied by some matrix, some weight, right? Multiplied by a weight, activate. That's how we get to our outputs here. And then these guys, these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these 10 outputs essentially determine what the ant is going to be doing. And we have that shown right down here, and we have that shown right down here. Okay, cool. Now I hope that gives you a sense of the brain class. Basically, we're feeding in a bunch of inputs into the ant. We take them all, we wrap them up into this array, and all we do is just fire that off to our neural network. We say, hey, please query your brain if, based on your synapses, based on what you've got going on in your brain, right? As a brain, as an ant, and then please send us back an array of outputs. And oh, by the way, brain, we need to have these 9 outputs that we can see here on the right hand side of the screen. And I'm just realizing now that the bottom of the neural network was cut off. So, wow. Let's see here if I do. Okay. What's up, bros? We are back here. I just checked on that video, made sure my face was not in the way of the text the entire time. That would have been super annoying to. We're moving on from our brain class over to our neural network here. This file was developed elsewhere for testing and pasted here, written by Brendan Robertson, based off of works and videos by Daniel Schiffman. So guys, I keep on imploring you to please go check out the coding train, Daniel Schiffman. He's got some freaking phenomenal videos on neural networks, on learning algorithms. Our neural network requires our input nodes M, our hidden nodes M, and our output nodes M. Basically, it just requires hidden nodes, input, and output nodes, right? Okay, those were the three things that we were seeing on this right-hand side, right above my head, right? Input, hidden, and output. Are we going to display the neural network? Currently false. Well, currently true because we are displaying it here on the right-hand side. That's all that does. In nodes, hidden nodes, out nodes. How many? Okay, so this guy actually has to do with key, and this actually has to do with number. And you'll see the constructor method when we build one. Either we're building it based off of a parent down here, right? We're passed in from the brain of an older ant, and we'll be showing you guys how to mutate that, or we'll be constructing a new neural network based on that, or we constructed a brand new one. This either happens when the population supply drops below 40, we'll be calling this method, or if or if we're initializing the game for the first time, that's when we're going to end up with this constructor pattern. So in any sort of neural network, you're going to end up with a learning rate. I think this again has to do with backpropagation. I don't think we use this in this. So let's go, we'll CFV, find. I do use it. I do use it during the training session. Oh, but I don't actually call train on this because I never need to train it. Yeah. So there is some code in here, which is awesome because and again, when I was building this, I wanted to go through the entire series by Daniel Schiffman there, because I just wanted to learn how neural networks worked. I wanted to learn, hey, if I had inputs. And I wanted to get some sort of output from, let's say, a classifier, right? Like the MNIST data set there. I could go ahead and I could still use this neural network to train it, and then maybe perhaps display this on in processing in this program for some reason, or just copy paste into a new program, and I wouldn't have to go ahead and rebuild it. Or I can use it in a genetic algorithm, like I'm doing right now, and basically not have to use learning rate, not have to use backpropagation, but I've built all of that functionality into this neural network. So it might seem a little bit bigger than what you're used to, but for genetic algorithm network, but still works. Okay. So yeah, let's go ahead and let's talk about. Have we talked about this? Yes. We have not. Okay, so input nodes. So when we're creating a new network for the very first time, our population drops below 40. Our input nodes are equal to the number of input nodes passed in. Very obvious here. Okay, and learning rate will default this to 0.1. The weights input to hidden, right? We're going to set up a new matrix of hidden nodes to input nodes. Okay, now this is an important concept to get because it's going to determine which way our matrix is laid out, right? So and again, these matrix functions are, I think, just essentially copy pasted from the Daniel Schiffman code there. And yeah, but we'll go ahead and we'll talk about these as well in a future video, not in this one. This one we're just going to be talking about the neural network class. So yeah, so these hidden nodes to input nodes. If we've got 50 hidden nodes, that's the middle layer over here. This only defines the shape of the matrix, not actually inserting values to our input nodes, right? And whereas this guy will be the output nodes to the hidden nodes. So you can see it's always the one layer over to the right being related back to the one on the left there, right? So WIH weights input to hidden, and then who weights hidden to output. Just keep the naming conventions a little bit shorter here. Input node matrix, new float, input nodes, hidden nodes, and output nodes, okay? So yeah, essentially just an array of inputs. All right. Randomizing the initial weights. So this is when I say that on day number 1, the ants are completely random. They don't know what they're doing because we've essentially just given them random weights. They haven't bred, they haven't learned, they haven't done much of anything yet. Down here, below the code while the game is running, we're going to be getting some debug information here. You can see another year has passed. Year 1, current info. The eldest ant currently, excuse me. The eldest ant currently is 328. So from an initial, is generation 5. So has learned 5 times, has spawned 7 ants. Highest generation is currently 12. So we do have a 12th generation. But not the oldest ant. So perhaps maybe not the best. Maybe this ant will be doing a little bit better. But these guys were more prone for breeding. So, whoever, maybe one of those species in the end will survive to the end. Yearly info, and then the highest spawn is currently 7. Okay. The yearly info. The highest spawn is 7. The highest generation this year is 12. All-time info. The highest spawn all time is 7. Longest generation to reproduce all time is 7. So this is just when we go back, we'll see that hopefully over time, this number down here, the longest generation to reproduce, will keep getting larger and larger and larger. So we see 12, we see 18. Down below off the screen here, it's 24, and then we see 25 down here. Now I don't know if this is the same ant collective that's building up the generations, but that's what's happening over time. And that's why we don't actually need to train, because this is a genetic algorithm. These guys are learning or they're dying. That's it. All right, building this neural network off of a neural network parent. We can just copy a new neural network, return this one. So perhaps the parent died. We'll grab that brain out of them first, we'll copy it, and then we'll generate a new neural network based on that for these kids, right? Yeah, and then that's why this is important, right? So the ant class or the breeding class or whatever will call out, the parent will say, hey, what's your neural network? Then when we're building the kid, we'll copy in their inputs hidden and their inputs hidden to output. Very important. Very, very important. And this guy could be, and this really could, it doesn't have to be your parent in nodes. It could just simply be, what is it called? Well, it could just be equal to our global class, but I didn't want to set it, I didn't want to tie it to our global class. I wanted to tie it to, because then you guys can actually pull this out and use this elsewhere. And then, you're not tying it to any sort of globals class that I've built. That's why I don't have it equal to that. All right. Display nodes, when you want to save the matrices for display, that's essentially what we're doing here on the right hand side. Otherwise we don't save the matrices. Hide nodes, display false. Okay. Mutate, very, very important. When we're creating when our parent breeds, when we give off our offspring, they're not clones of us, right? We do have to mutate them a little bit, and this is what's going to help them learn and succeed. You might think, this ant's doing really well, we just want to create copies of it. Well, we maybe haven't found the exact solution that will solve the problem of living in this environment with this grass that's changing all the time and these other ants that are out there. So we do have to mutate the matrix again and again and again and try and do that. Okay, so train. So not sure if I will use this. Brendan, you're absolutely correct. Pass Brendan, good job. You don't use that. We don't use that because we're doing a genetic algorithm. But querying the network, this is important. This is what we do use for sure. All right, guys. So what I was saying earlier, this is important. This is what essentially gives us how to move around the world. This will give us our outputs based on our inputs there, right? And again, I'm just going to tell you, I'm going to 2 caveats here. 1, this is not important. I use that for backpropagation. But we're not doing backpropagation, we're only going forward. This is a genetic algorithm. It's not a network that we are training on a set of data, saying, is this number 1, and it'll say this is 2, and we'll say, no, that's wrong. And then we'll have to go backpropagate to calculate the error, but we don't do that. The ants either live or they die in this environment. Our inputs, right? This is a one-liner function in our brain class, but we're actually gonna go through and see how it works, right? So we get all of our inputs, as you remember, and then we call query on our brain class, which is in fact our neural network class. And we start off by creating matrices, because all of this is done with matrices. It's not done with arrays. Matrices you could, I guess, think of as multiple arrays in a row, but they're not. And we can do like dot product multiplication on them, division, addition, subtraction, all of that good stuff. You guys can go check out the course by Daniel Schiffman on this, or you can, if you have the GitHub open, you've got the code open in front of you, you can scroll on down and see how I'm doing this down here. Okay, so very important. Number one, turn your inputs into a matrix. That's going to be very important for us to be able to do dot matrix multiplication. And it's also going to be very important for our activation functions here as well. Well, maybe not so much for our activation functions, but it is important so that we can just take a series of inputs, multiply it by our synapses, and get our hidden nodes, right? So let's see here. First, we get the inputs from the two arrays. So we'll multiply. First you multiply, then we activate. We're going through, I think we're using tanh here. We could use sigmoid, but I decided to use tanh. There's talks now in the community that leaky ReLU, which is this function down here, is getting better performances when you're doing backpropagation. I haven't tested out the difference between the two yet. I haven't implemented this. I've only implemented tanh, which gives us an output between -1 and 1, and a sigmoid, which I think is between a 0 and a 1. Whereas leaky ReLU would give us negative infinity to positive infinity. So these are all just different activation functions. The important thing is that they're non-linear, and that we can actually calculate, we can backpropagate through them. But again, genetic algorithm, we're not doing backpropagation. I think I've beaten that point to death, but I don't know. I guess I'm saying it again in case you guys skipped ahead to this part of the video. All right, and then and then we're gonna multiply. We're gonna get our output inputs, and by that I really just mean we're gonna get 1, 2, 3, 4, 5, 6, 7, 8, 9. We're gonna get these outputs based on a multiplication of our hidden nodes and these right-hand synapses, right? Or our WHO, weights, hidden, outputs. Weights from the hidden to the outputs, right? So first you do your dot matrix, and then you activate. I do use the tanh here, although it would be just fine to use the sigmoid as well. There's no rule out there that says you have to use the same activation function when you go from layer to layer. Okay, and then if this dot display, this is where these properties come into play. Input nodes, M input nodes, M input nodes. Yeah, matrix, matrix, matrix. Yeah, inputs to arrays. We're converting our. Keep clicking on this over here. I shouldn't be clicking on this because it keeps going away. We're converting this matrix, this one-dimensional matrix, to a one-dimensional array. Same thing with our hidden, and same thing with our output, and we're passing that on to our display class, or it will be called from our display class, from our GUIs. Okay, and then we're going to return our outputs to array, which are essentially these 1, 2, 3, 4, 5, 6, 7, 9, these 9 outputs here on the right-hand side. And if we click on something that's living, you can see that they're changing all the time. And basically that's going from our input. You can see this one down here. There's a few of them that are changing. But yeah, and then how does this ant learn? Well, the synapses between the input and the hidden and the output determine what it does, where it moves. And the reason that everyone says, or I say, that these guys are essentially random when we first boot up the game is because all of these synapses are initialized as random. Hey guys, I'll do a quick channel update at the end of this, but let's just go over and review what we've covered. So we covered up the brain class here. We got to see how the ant can talk through this input component to the brain class, and all that good stuff, how it gets its inputs. Did we ever actually cover how it uses the outputs? Essentially the outputs, the 9 of them, they're just fed into here. I say if you're greater than this, do this. If you're less than this, do this, right? That's it. So it has to learn to put something above 1 or below 1, or if it's between something, it'll grow or shrink something, move in a certain direction. And yeah, the neural net just has to learn to work with these sets of rules. based on the input, and then that's how it moves around. That's how it does stuff. Oh, I do have a memory. Interesting. Do I feed that into the inputs? Memory 1 and memory 2. Interesting. I don't think I do actually. No, I could put the memory in there. I could put the memory back in. Then I have to do that. Okay, well, you know what? I'll do some testing here for the next episode and see if that helps the ants learn a little bit quicker. Because yeah, currently they're not learning very fast, and it'd be nice if they learned a little bit faster how to go ahead and do this. Quick recap. Yeah, so the brain class. Then we covered the neural network. Basically, the most important thing is how we're querying our network. We didn't really talk about the matrix class, and I don't think we will. If you got the GitHub open and the project file open, you can go down here and check out these matrices and see how we're essentially doing the randomize, the multiply, what's dot product, what are adding two matrices together. So review done. Channel update on. First week of posting is over. I'm super pumped. The results are awesome. I think we've got 6 new subscribers over the week, so thank you so much. Channel views are up. Thank you guys again so much. This has just been awesome. I've got a microphone now, so hopefully the sound quality starts getting up there. You guys can expect some. Oh, the first cycling video was posted. That was a lot of fun. I'm going to be starting to post maybe once a week different cycling rides that I do and turning those into workouts. Currently I'm coaching the UBC triathlon team, just the track portion. I was a triathlete for 4 or 5 years as part of a development squad in Alberta, and I've just been like active all my life, so I hope I can give you guys some cool workouts. If you're into cycling, if you're another thing, if you're not, don't worry about it. Sorry, I'm spamming your inbox there with cycling workouts then. What else? Yes, writing more comedy sketches here. So I am working on that. We should hopefully see the next one by this weekend. And other than that, just thank you guys so much for all this feedback, the likes, the comments, and just keep on talking, just keep on helping me out here. It really encourages me every time you guys, just give even a brief shout out. That's huge. So thank you guys so much, and I'll talk to you guys in the next episode. Okay, later. Bye.